So today we got Jack coming from Cambridge, but he's also visiting Cornell for this semester. He's going to talk about his latest breakthrough result, which is a zero-knowledge PCP theorem. So please take it away.
And thanks for having me. Thanks for coming. So I'm going to talk about this work today. It's a joint work with Tom, my supervisor, and Nick, who I mentioned, who's in Cornell. Please, throughout the talk, just stop me. We've got a small group, so in general, I'll have you get questions, but we can be very interactive. Make sure, please stop me. Okay, so I'm going to start off by introducing what PCPs are. So the PCP part of zero-knowledge PCP. So what is a PCP? Well, the best thing to keep in mind is the verifier definition of NP. Okay, so we have some verifier. They're going to get some input X, and their goal in life is to decide if X is in some language L or not. Okay, but this will hopefully be all familiar to everybody. And then they're going to accept if X is in the language and reject if it's not in the language. Okay. And they're going to also get access to some witness or some proof. Okay. So in the NP case, they're if the input's in the language and they get the right witness, they will always accept. And if they get the wrong proof or the input's not in the language, they'll reject. Right. Okay. Probabilistically checkable proofs generalize this in a couple of ways. Okay. So the first thing is we're going to let the verifier be random. Okay. So now the verifier, instead of reading the entire proof, they're going to kind of pick some locations. So we can kind of think of them as having an oracle to the proof, right? Rather than reading the entire witness, they're going to have an oracle to it. And then they still want this. We want these same guarantees that they accept or reject if X is in the language or not. Okay. But since we're kind of dealing with some randomness, we're going to kind of relax our definitions for what we call completeness and soundness. And we're going to say, that if the input's in the language, then you should accept with high probability. And if the input's not in the language, then you should reject with high probability, no matter what witness or proof you see. Okay. So we're instead of thinking about the witness, we're going to now think about the proof. Okay. Is everybody okay with this so far?
Yeah. So is the proof just an oracle, or
it's so you can think about this thing as being like a string of bits, and you can and you have an oracle to this string where you can query locations of the string. Does that make sense?
So why don't you just query the entire string? Is it too long?
Yeah, so you can think about it as being too long. So in some settings it is too long. This thing will be polynomially long, but what we're going to get is that you're going to be able to query constantly many locations of this. So you won't actually need to read any substantial fraction of it at all. This is kind of the gain that we get is we blow the proof length up a small bit, but now instead of having to read the entire witness, we just read some constant number of locations of this proof.
Okay.
Does that make sense?
Yeah.
Yeah. Okay. Good question. Thanks. Is there anything else that I want to say about this? And I kind of said you can think about the proof as being bits. You can think about it as being bits, but it's probably going to be field elements in the talk. But we'll get to that when we get to it. You can think about this as being a string over some alphabet that you can just query locations of. Okay. There are two complexity measures that we're going to care about. So the first one that we just talked about, which is the query complexity. So how many queries does the verifier need to make to the proof string in order to do its verification procedure? Okay, we want this to be low, right? We want to read as little as possible. And the other thing is the proof length. So how long does this proof need to be, right? So kind of you can think about, you have some witness, which is of some length, and you're going to kind of map it to some proof, and you want to think how short can the proof be, right? You obviously want the proof to be short as well. Okay. And the last thing I'll mention about this is just to define what I mean by adaptive or non-adaptive, because this is going to come up in the talk. So an adaptive or a non-adaptive verifier is one who kind of flips some coins and at the very beginning can decide all the locations are going to look at in the proof just in one go. An adaptive verifier, in contrast, is one who flips some coins, looks at a location, and then depending on what outcome they see, they decide where to go next. Okay, is this clear? This is pretty standard definition, but I just want to make sure everyone's okay, cool. So that's what PCPs are. No more questions on the model. We're happy with what PCPs are? Good, okay. So I'll quickly state the classical PCP theorem from the 90s. So it says it's a beautiful result. It's super, super cool. It says that, for any language in NP, you have a PCP, which is polynomial length. So you're only blowing up the witness by a polynomial factor. And you only require a constant number of queries to verify it. Okay. It has connections to hardness or approximation. It's a super cool result. So today we're going to try and get a zero knowledge kind of version of this result. Okay. Okay. So now we're going to define what zero knowledge PCPs are. Okay. So what does zero knowledge mean? So zero knowledge, like kind of at a high level, means that you don't learn anything. When you interact with the proof, you shouldn't learn anything other than the input is in the language, right? You shouldn't learn anything additional. Okay. So we need to formalize that somehow. Okay. So the way that we're going to formalize that, or actually before I say that, what I want to say is when we say you shouldn't learn anything, you can think about having the verifier who interacts with the proof in the way that they're supposed to, right? So in the previous slide, we talked about a PCP, and there's some verifier who has there's some algorithm that they're supposed to run on the PCP to inspect the PCP. Okay. You could argue that they don't learn anything when they look at the proof, right? This would be some sort of a guarantee. Really what you would want is that no matter how, once you send the proof as an oracle to the verifier, once you give them a string, no matter how they look at it, they still shouldn't learn anything, right? I'm still being wishy-washy here and talking kind of hand-wavy. I'm going to get formal in a second, right? But this is kind of a notion of like a malicious verifier, right? Or an adversarial verifier. So Mr. Dastardly here is our malicious verifier, right? And he is going to inspect the proof, and he's going to inspect it as he pleases. And we're going to ask that no matter how he inspects the proof, he still can't learn anything. Okay. Okay. We're going to there's going to be a small caveat on what he can do, but for now you can think about it as PPT, like polytime. Okay, for now. We're going to slightly restrict him in a second, not yet. So how do we formalize this? Well, the way we formalize this is he shouldn't learn anything more than what he sees when he inspects the proof. Well, one way of formalizing that is to say, or the way we formalize that is to say that there exists an algorithm which has the same powers as Mr. Dastardly. Okay, so it's also PPT. And it's going to produce answers that look like the answers he sees when he interacts with the real proof. Okay? And the point is that he could have just run this algorithm himself. So importantly, when you write the proof down, you need to know the NP witness. Right? We can keep NP in your head throughout this talk, right? We're going to be kind of thinking about NP. So to write the actual proof, you need an NP witness. This simulator has the same powers as Mr. Dastardly, so he doesn't have the witness. Okay? The power we give the simulator to allow it to do this is we allow it to answer adaptively. So the real proof, when the prover writes it down, they have to commit to the whole thing in one go, right? And then you're allowed to start querying. The simulator is allowed to make it up as it goes along. Right? So you say, I want to know what's the value here, and the simulator goes, oh, it's a 0. And then you go, what's the value here? And the simulator goes, oh, it's a 1. But it doesn't have to commit to the whole thing in one go because it couldn't do that because it doesn't have the witness. Okay. Is this much clearer? Yeah, okay. There's a couple of subtleties I need to talk about. So the first thing is that this proof needs to be chosen randomly. So if you've seen the PCP theorem before, or PCPs, these proofs are typically like a deterministic encoding, just in case anyone has that in their head. For zero knowledge, you can show that this is true in zero knowledge in general, like even outside of PCPs, if you don't have randomness, you can't do anything. So you can show that if you if this proof is not chosen randomly, you can only do trivial things like BPP. Basically, you can show this formula. So you need randomness. And the other thing is the caveat on our adversary, which is that he can only make up to Q star, some bound number of queries to the proof. Okay. So we can think about him as polytime, but he has there's a cap on how many locations he's allowed to look at. The reason that this is the case is because, say for a minute that he queries the entire proof. So if the proof is a PCP, it's going to be complete and sound, right? So it's going to have to be convincing. And informally, for this to be the case, it kind of necessarily has to encode something about the NP witness. So if you read the entire proof, you kind of have to learn something about the witness, which we don't want to be the case. You can show formally that if I let you query the whole proof, you're only going to get BPP again. Okay. So for the model to kind of be able to do anything at all, you have to query bound your adversary. Okay. So what this query is saying is that my proof is zero knowledge as long as you only look at up to Q star locations, right? And what my simulator will be able to do is answer as if you are the real proof up to Q star queries. Okay. And then the last thing to say is just what we want is that the output of the simulator looks like the output of the real protocol. Depending on how close these things are, we have different different notions of CK. But today we're going to talk about perfect zero knowledge, which just means that these two things will be identically distributed. Okay.
So why is it impossible for there to be a witness that only tells that it's in the language but does not tell what the object is?
The point is that you can kind of if you like that basically, if I give you a proof that comes from a witness, you can kind of like reverse engineer the witness back out of the proof. And the witness, like learning the witness. So think about like, you know, if it's three coloring, right? Like if I want to prove to you a graph is three colorable, if I give you the witness, if I give you the coloring, that's something more than just like convincing you that the graph is three colorable. It's giving you the coloring, right?
Yeah.
So if you could figure out the coloring from the proof, that would not be zero knowledge.
I see.
So you can show that any such proof, if you can read the whole thing, you're able to kind of work backwards and get the witness out. So you would learn, like learning the witness. Like I want to convince you of like, you know, membership in entity without revealing the witness. I also don't reveal anything else that you couldn't compute before yourself. But like most importantly, kind of in a sense, keep your head as the witness. Does that make sense? Yeah. Okay. Any more questions? Yeah. It's a subtle model, so it's worth. Yeah. Okay. So this is the important thing to keep in mind in this query bound. Okay. Good. So, quickly I'll mention some prior work. So the first piece of prior work on zero knowledge PCPs by Killian, Trank, and Tardish from 1997. And they get PCPs for NP. Oh, sorry, one more thing I want to say on this model really quickly. Sorry, this is kind of a little bit confusing. So I said earlier that like the verifier can be adaptive or non-adaptive. And in the PCP theorem, the honest verifier, like the verifier who goes and like does the PCP verification, is non-adaptive, which is good because it's a weaker verifier, right? When we're thinking about this malicious verifier, we always assume the malicious verifier is adaptive. We're assuming the malicious verifier is as powerful as we can kind of make them up to this query bounds. They can make these queries whatever they like. Okay. Okay, good. So when I talk about adaptive or non-adaptive on this slide, what I mean is the honest verifier, right? Because the malicious verifier is always going to be adaptive. Okay. Right. So Killian, Trank, and Tardish get this like get these PCPs for NP. They get polynomial proof length, which is the same as the PCP theorem. They get polylog query complexity. PCP theorem was constant, so this is worse. They get a polynomial query bound, which is good because the proof length is polynomial, so you kind of can't hope for better. Like this is how many queries you can make to get CK. The zero knowledge type they get a statistical, so you can hope for perfect, but this is quite good. And the honest verifier is non-adaptive, which is a bad thing. Then there's some other work by Yuval Shai and Weiss and Yang, I think. And the point of this kind of line of work is all about trying to like get rid of this non-adaptive problem, make the verifier, the honest verifier, non-adaptive. Because if you're thinking about cryptography, they're kind of motivated by cryptography. So they're kind of trying, you know, if you've got an adaptive verifier, this is like honest verifier, this kind of results in like interaction stuff. It's quite bad if you're trying to like roll this stuff out. So they get rid of this adaptivity problem, but they completely lose zero knowledge and get witness indistinguishability instead, which is a much, much weaker guarantee. And the rest of their parameters are still kind of the same. And then there's another piece of work along the same line by Harmit, Mushu, and Weiss, where they want to try and fix the zero knowledge. So they get back to statistical zero knowledge. They keep this non-activity, but now they're like their query complexity and query bound is quite bad. So like they're getting like for some small constant. They're like this is like their kind of query complexity, which is like much worse than polylog, right? Like it's bigger than polylog. But also another problem with this work is just like the kind of gap between the query bound and the honest. So this is how many queries the honest verifier has to make. This is how many queries you're secure against. And this is like a quadratic difference. So like you don't get like an exponential gap between your honest party and your adversary. It's kind of just not good. So what do we do? So we prove what you can kind of think of as like a zero knowledge PCP theorem. So we show that for any query bound up to like exponential, NP is perfect zero knowledge PCPs, where the proof length is poly in the query bound and the instance size. I'm going to give you a nice parameterization in a second. Get constant query complexity and non-adaptive verification. And to kind of make this a bit more concrete, if we plug in, if we set Q to be a polynomial in N, then you get poly-sized PCPs for NP, which have constant query complexity and a polynomial query bound. Okay, so like both of these parameters before the query bound are the same as the PCP theorem, and the query bound is poly, right? So this is our main result. Okay. We also show this scales up. So like the classical work on PCPs, you can also get like a PCP theorem for NEXP. So we get the same thing, that like you can get PCPs for NEXP where you have exponential proof length, and like this makes sense because the witness for NEXP is exponentially long. You still get constant query complexity, you still have non-vector verification, and now the query bound is exponential. Okay, so we kind of get both regimes. In the talk, I'm going to think about NP mostly. It's just a rescaling. Yeah, and then to kind of put that into the chart, I left out the next one, but like this is what we get basically. So we kind of, I mean, I've picked the colors to make all of our green, but yeah.
And this is the combination of two works.
Exactly. So on the slide, I'm going to delineate between the two. I'm only going to talk about one of the works today. So I'm not actually going to talk about the kind of full results. I'm going to kind of give a technical overview of kind of the first paper, which doesn't go the whole way, but I can talk a bit about it afterwards. Yeah. Are there any questions on the statement of the results or anything before I move on and talk about some, I think, or even earlier stuff that you've now are confused about now that I've mentioned all of these different parameters? There's a lot of parameters floating around, so if anyone's unclear, please stop.
There's always whenever it's presented, there's always like, is there an improvement on this? It looks like there is. Have you just sealed the deal on this? Or
is there? Yeah, I mean, there is an improvement. So one thing you can do, I mean, I'll talk about this at the end, or I'll mention it. This is from my very last slide. I'll mention it, but there are things you can think about. Like one thing is driving this proof length down. So there are actually PCPs for NP. So Ben Sassan, Sudan in 2008 got some PCPs where you get sublinear proof length. And still get constants, blah, blah, blah. Well, yeah, they originally kind of only, yeah, it doesn't matter. Yeah, they get constants. So this is like, and the techniques that like, we're kind of generalizing sum check to do this, like kind of the sum checky approach to I'll talk what that is if people don't know what it is. Whereas the techniques used in this are they're still algebraic, they're very different. So it's not clear at all that you can use our, yes, there are more questions. There are more questions.
Yeah. You mean like quasi-linear or sublinear? The proof length.
Oh, sorry. I mean quasi-linear. Sorry, not sublinear. Quasi-linear. I mean quasi-linear. Yeah, like n log n. Yeah, not sublinear. Yeah. So like you don't have to really blow up the witness size at all. Yeah. Obviously sublinear is not possible. Yeah.
And you get like what's the constant here? You feel it could be driven down
in hours?
Yeah.
I actually don't know. I think it's quite big. You probably could like do some stuff to make it smaller. It's a good question. Yeah, I guess I very much think in asymptotic, so I don't know off the top of my head what the constant is, but I would imagine it's big. I would imagine it's be a question don't ask. Yeah. But sorry, I can't give a better answer. Yeah. And I guess like another question as well is like, can you generally transform a PCP into a zero knowledge PCP? Right? Like, is there some general transformation that just works for all of them? Like, because like we get the PCP theorem for free, right? But you know, can you do something for anything, right? Because like Irit Dinur's construction from like 2005, like it's very combinatorial. It's a very so she also proves the PCP theorem for anybody who doesn't know, and she goes about it a completely different ways to kind of so we're kind of going to go through a bit of how they do the original proof from the 90s, but she goes about it a totally different way, and you can do different stuff than with what she gets, and in particular the work that I just spoke about, the Ben Sassan Sudan thing, the kind of the quasi-linear stuff. If you want to get constant query complexity for that, you have to use her work to do it. So like you might hope that she could somehow maybe use our techniques to like get all of this the same except quasi-linear here, but this would be polylog without using her work. But her stuff it's very combinatorial, so it's very different. Like it's you know, there might be some hope you can do something algebraic, but this whole other thing, but maybe you can, right? So yeah. Okay. So I can talk a bit about the technical stuff. Yeah, cool. Okay. So yeah, as I kind of just mentioned, this is kind of like there's two works. So the first work from like a year ago, or maybe a bit more now, is showing that you can get PZK PCPs for sharp P. So sharp P is a complexity class, like counting NP. So for anybody who doesn't know, like in NP, I give you a CNF or something, and I ask you, you know, like how many, or I ask you, does it have a satisfying assignment? And in sharp P, I just ask you to tell me how many satisfying assignments it has. Okay. So this is like strictly harder. So in the first work we showed that you can get perfect zero knowledge PCPs for this class. Okay. And that's what I'm going to mostly talk about today. Then kind of the way that kind of classical like PCP theorem was shown was the first thing they did was they kind of like once they got this, they then showed how to use that to get PCPs. If you just remove PZK from all these points, it's kind of how they did it back in the 90s. So like they get PCPs for NP, where you have polylog query complexity, and then they do a thing called proof composition to get this down to constant query complexity. And we pretty much follow the same blueprint, but like at every point you have to preserve zero knowledge and like do work a lot harder. So today, what I'm going to talk about is this first box. So it's the first paper. Okay, I'm happy to talk about this afterwards. People want to chat about it, but this, I think most of the cool ideas, or most of the kind of the new fun ideas are in this. So we'll talk about this. So that's going to be our goal. So we're going to try and get a perfect zero knowledge PCP for sharp stat, okay, which is just counting stat. So what is that? I give you a CNF, and I ask, is n the number? So this is like a decision variant of sharp stat. Is n the number of satisfying assignments of this CNF? Okay, hopefully people have seen this before. And there's some work from the 90s, like the sum check paper at FKN. They show that this reduces to sharp stats, what I'm calling sharp stat sub f, which is this is like using arithmetization, if people have seen this before. So this isn't going to be super important for the talk, but effectively what you can do is you can take a CNF and there's some way to convert it into a low degree polynomial, right? And this polynomial will basically like when you plug in values on the hypercube, like bit strings, it will like be true to the CNF, it will agree with it. But what the extra power is that now you're allowed to plug in like elements from the field. So you've got some finite field. You can think about the field as being big, like something like whatever the size of your CNF is, like think of the field as being like the size of that to the 4 or something like that, like something pretty big. The soundness of all your protocols is going to depend on how big the field is. The bigger you make it, the more soundness you're going to get. And you basically now you've got this polynomial and you ask, does the polynomial sum up to n? Because the polynomial is degree with the CNF. Okay, and this is like some low degree polynomial. And what did we gain? We gained the fact that like polynomials are an error correcting code. So this is going to allow us to do a bunch of stuff. Okay. So we're not actually going to quite work with this. I'm going to simplify this one more step. So this is equivalent, but there is actually a reduction. My next step, there isn't a reduction. Oh, I should also say, sorry, yeah. You could think here as having like an oracle to P, right? So you're going to be querying P and you're going to be asking like, you know, like, does it sum up to n, right? So in particular, to do this without the help of a prover, you need to make 2 to the m many queries. You just need to query everything, okay? Right. Okay, good. So, right. So what I'll say now is that we're going to simplify this a little bit. This is not equivalent, but for the purposes of the talk, I can draw pictures here. Like the thing I just mentioned is like n-dimensional. So what we're going to think about now is like a 2-dimensional variant of it. So I'm going to give you, and like all the ideas that like you have to use to solve the full n-dimensional thing, like work here, right? With a couple of adjustments. So I'm going to give you a polynomial, which is low degree. I'll explain what I mean by low degree in a second. It's bivariate, it's over 2 variables. And we want to ask, is it sum over like an m by, I've got a picture, she'll put up. Is it sum over this like m by m squared equal to n, okay? If you didn't follow anything on the last slide, this problem is like, we're going to go from here. So this is, if you pick up here, you're okay. Okay, so I give you a polynomial, and I say it's low degree in the sense that the degree is somewhere in between the size of f and n. So if you query like the m by m squared, that's not enough to interpolate the whole polynomial. There's still kind of some slack there. But if you wanted to interpolate the whole polynomial, you wouldn't need to query all of f, right? You kind of could stop somewhere in the middle. You could have enough information, okay? So this is the problem we're going to try and solve, okay? So if you don't have a prover, you're going to need to make like m squared queries, right? You just got no hope. You can't interpolate the polynomial because you need to make more than m squared queries to interpolate it. So you just need to make m by m, just query the square. Is this clear? Okay. So now what's going to happen is I'm going to give you a proof. And our goal is going to be that the verifier makes linear and n queries to both the proof and the input polynomial. Okay. So we're going to make a quadratic saving. And we're also going to try and do this in zero knowledge, right? That's kind of, so like, if you're looking at this, you should be thinking sum check. If you've seen sum check before, it's going to happen. I'm going to explain sum check though from scratch, so don't worry if you haven't. But now we need to define what we mean by zero knowledge here. So what zero knowledge is going to mean is like, okay, the simulator should have like the same powers as the verifier. So the simulator is going to also have an oracle to P, but it doesn't get an oracle to pi. It doesn't raise, it can't know the proof, it isn't the prover. And its job is going to be to like simulate access to the proof. And it needs to use like big O of the number of queries you make to the proof to this to simulate that. And the reason we make it like, so normally for zero knowledge, we would kind of say this big O would be a poly. But as soon as you give the simulator like a quadratic boost, it's able to kind of go and query this. It can do things like query the square, which are bad, right? Like if you make m queries and it's allowed to make m squared queries, then like, you know, it can just like figure out the sum, which you couldn't do. Does this make sense? Yeah. Okay. Are there any questions on this? Is this? Please feel free to, I can just go over it again if people aren't clear, okay.
So what's the runtime of the simulator here?
Yeah, okay. So I mean, I haven't given you a simulator, but you can think about the simulator as being PPT. So you can think about every like, okay, I guess runtime isn't even that important because we're kind of thinking about all these things as being poly-sized. So like the simulator kind of has time to like, it would have time to like read the entire polynomial because it's not that big. But the point is that like we're thinking about like our query bound. So you're only allowed to look at like up to m entries of, up to q star entries of p.
Right.
And you need to like kind of like simulate, so like the view of the proof, only making like big old q star queries to the proof.
Yes.
Right. So like the verifier is going to come along and they're going to say, I want like for up to q star locations, they're going to say, I want to know what the value is here and here and here and here. And the simulator can only make like a constant multiple of that many queries to p to like output a faithful a faithful simulation.
Okay.
Does that make sense?
Yeah.
And like if you allow the simulator to query more than that, say for example you make m queries, now the simulator can make m squared queries. So it's able to like actually just query the entire square.
Yeah.
So it can figure out something that you can't figure out, right? It's actually able to just compute the sum itself. Okay. So this is the problem that we're going to solve today. We're going to, yeah.
Is it like D is the degree of the polynomial and is larger than m squared?
Okay, the individual degree of the polynomial will be like bigger than m. So like the degree in each variable, in both the variables, right, will be like somewhere bigger than m, but less than f.
Yeah.
Right, kind of anywhere in between, doesn't really matter as long as it's a bit bigger. Yeah.
So for stat f in the previous slide, you had this x in like x was 0, 1 for m, and here you went to m.
Yeah. I mean, this is not equivalent. Like I'm not claiming that you can reduce the previous slide to this.
Okay.
But like somehow the same ideas work. So like what will really be going on is like this kind of gives you some saving in the sense that you get this like quadratic saving because you're able to kind of what we're gonna achieve this goal, right? We're gonna be able to do it in all of m when really it's m squared. But somehow what happens in the real protocol and like what happens in some check is like you repeat what we're gonna do many times. You do it like once for every dimension.
Yeah.
And then you get the whole thing, and then you get like this exponential speed up. But we're just, this is not equivalent. It's just like a nice picture that looks, but all the ideas like work without any real modification in the full thing. Yeah. But I'm not saying this is a reduction or anything. Yeah. Okay. Okay. Any more questions? Okay. So now I'm going to explain some check in this just from scratch. So this is from the 90s. So this is a way to, so we're going to forget about zero knowledge for a second completely. Just how do we achieve the first line of the goal? Like we're going to try and do this in like O of m queries to the proof and the input. Okay. So we have our input P, which we've got our oracle to, and the prover. And we want to verify, that the sum over like the n by m square is n. If you like equations, it's an equation, but the picture is fine. And we're going to get given some proof. So what's going to be in this proof? So what the prover is going to do is they're going to write down these row sums. So they're going to like sum up this pink band, like the first row, and that will be the first entry of pi. The second entry will be the next row sum. The third entry will be the third row sum. And these sums stop at n, but we kind of go the whole way down the column. So we write down like all these sums. Okay. So, and like this is just an equation for what this is, but like and the picture is good. So pi is going to consist of like sums of the first m entries of each row. Okay. Now, why does this help? Well, what's V going to do? V is going to first check that if we sum up the first m entries of the thing it got sent, that adds up to n, which is what we want to check it adds up to. Okay. So that requires m queries. But obviously now we haven't actually checked the input of one, right? We've only checked the proof. So we haven't, like, this isn't a valid check yet. Okay. So if we trusted the prover, we'd be done, right? Like we'd have done it in O of m queries, but we don't trust the prover. So what we're going to do is we're also going to pick a row randomly, one of these rows at random, and check if it agrees. Okay. And this is where the low degree polynomial structure comes in. So if we just had the m by m square and we didn't have all this extra stuff, right? The only way to verify that all those sums were correct would be to go and check every single sum, because the prover could lie on one of the sums, right? But now polynomials form an error correcting code. So what we have is we have this row, or we pick a random row, and the point is that, okay, imagine for a second that the prover lied. Right, actually, well, make sure this, well, first of all, we'll say is like, this is, if the prover is being honest, right, this all works, right? Like, if the prover is being honest, then this sum really adds up to n. So they're going to write down all the row sums, and the green bar is going to sum up to n. We're going to be good, and any row, like all the rows will be correct. So any random row will pass. So we're good, right, in that case. What if the prover's lying? Prover's lying, his sum in this n by m square is not equal to n, right? So the prover could be really silly and like and just write the honest sums down. And then when we check the green bar, it would fail. So we just catch them. So they're not going to do that. So let's say they make this something else. Well, the point is that like, say for a second, this is a polynomial, but this has to be a polynomial. Right? If the prover is fixed, they have to write down a polynomial. When the prover writes a polynomial here, if they want to make it something other than the real sums, it's going to be a different polynomial to the real polynomial. And when two polynomials are different, they differ basically everywhere because they're an error correcting code, right? They're like two code words in a code. They're different in lots of places, which means that it's sufficient to just check agreement on one location. We get like a high probability that we'll catch the proof if they're lying. Okay. And then the only kind of loose end is, well, what if they don't send us a polynomial? We have low degree tests from the 90s that let us check if this thing is a polynomial. Okay. So for the rest of it, and we don't need to fix those at all. They're inherently zero knowledge. Like, you know, you look at the proof, you don't do anything with the input, right? You just check if this thing is a low degree polynomial. So we can check that. For the rest of the talk, we'll just assume everything is low degree because you can always check it is. So this is sufficient. Okay. Is this clear? So this is all that goes on. Like if anyone's seen sum check before, usually you see it like this kind of like long-winded, like, you know, multiple layers of recursion way. This is like one layer of recursion of sum check. That's all we're doing. You can do it in more generality than this, but this is enough for this talk today. Okay. So we got completeness because, like I said, if the prover's honest, everything works. We also got soundness because provided this thing is a polynomial, if this does not add up to the right thing, or if this doesn't add up to n, then the prover has to write some other polynomial here, which will be far. So one random check is enough to catch them. And we didn't get zero knowledge. And the reason we didn't get zero knowledge is because, if I wanted to compute any entry of pi, right? If I wanted to simulate any entry of pi, all I can do is go and compute the actual row. So I have to make m queries, right? Like for any of these rows, this thing here is a row sum of this stuff. So the only way to figure out what that should be is to go to the input, make m queries, query the entire row, tot them up, and output the correct value, right? But this is making one query to the proof requires m queries to the input to simulate. This is bad, right? We wanted only a linear blow up in the simulation. Okay, this is not zero knowledge. Okay, so our first idea is going to be based on this paper from 2017 by Ben Hassan, Chiesa, Ford, Amazon, forgetting the R at Spooner, and Ryabzev, which is this idea of adding a random mask. Okay, so this isn't going to work. This is the first attempt. So what we're going to do is, here's our input that we're trying to tot up the sums of. The prover is going to write down a random polynomial, a random low degree polynomial, which is supposed to sum to 0 on the hypercube or on the m by m square. Okay, so if we were to add this thing onto p, we wouldn't affect the sum. Okay, now it's important to note that even though this thing sums to 0 on the m by m square, it is non-zero on the m by m square, right? With almost certainty, it's like just its sum has to be 0. Okay, and then what we write down is what I'm going to call pi sigma, which is going to be like the same sum check thing we just did a minute ago, but now we're going to do it for p plus r. So the first entry of pi will be you know, the row sum of P plus the row sum of R, and so on. Okay. So, if we work off the assumption that like, well, actually we won't even do that. So like, you know, this is complete because if the prover is honest, or, yeah, say this is our PCP. So our PCP now doesn't just consist of this thing; it also consists of like writing down like this function. Okay, so we've made our PCP bigger, but you know, not that much bigger. And I'm also going to change notation because I want to just yes, I'm gonna use this like sigma of P plus R notation to mean the sums of P plus R. Right, the rest of the top, which stop me if anything's not clear. Okay, just to be consistent because these row sums are going to come up quite a bit. Okay, so it's complete because like, you know, the sum of the square on P plus the sum of the square on R is equal to whatever this is plus 0. So we just do all the same checks as before. Okay. I'm going to briefly skip soundness, which is ominous. You know, soundness is not going to work. But zero knowledge actually does work. Okay. So the reason this is zero knowledge is the following. So actually, I'll even go back and kind of give a bit of an intuitive reason. So kind of like, I'm going to give a formal argument in a second, but like, imagine you were looking at this proof and you wanted to work out something that was hard to simulate. So kind of what we've said in the previous slide that's hard to simulate is like these row sums. You kind of need to hide these somehow, right? Like, because they require n queries to get. So say, you know, you query the bottom row here. Now what you get is like this plus this, right? This is pretty much random stuff, right? It's all random. So you basically like, to kind of get this sum back, you need to start querying this stuff to kind of strip away the randomness, kind of one like entry at a time, okay? So if you were to strip away this whole row, like it's not quite as simple as this because there's low degree structure, it's a polynomial, but you know, if we just assume it's something uniformly random for a second, if by the time you stripped away this whole row, you made n queries here and one query here, right? Now the simulator has the budget to go and make m queries over here, right? Because you've made n plus 1 queries to the proof. So it's allowed to make m queries to the input. So like it's trying to tell you what this sum is. Like until you make n plus 1 queries, it doesn't need to know. Everything's kind of random. You haven't learned anything yet. And then when you get to, I'm going to kind of formalize this in a second, but like this is effectively what's going on, right? Okay, so slightly more formally, how could you simulate this? Well, you can pick, you know, you're the simulator, you write down a bivariate polynomial, uniformly random, which sums to n, which is what the input's supposed to sum to, okay? So you just write that whole thing down, right, privately. Like you don't need to query P at all to do this, you just write it down. This is like some poly-sized object, you just write down. Okay, and then you write down its row sums, okay? Now these row sums are distributed correctly, right? Because P plus R is a fixed polynomial plus a random polynomial that's supposed to sum to 0. So it's the sums of a random polynomial that sums to n. So this looks right. So we're kind of good on that one. That. Now P or R is also part of the proof. So we need to like somehow simulate that. But if you think Q is kind of representing P plus R, so what we need to get out is R. So R is equal to like Q minus P. Or is it P minus? Yeah, Q minus P. Right, so whenever we want to like get an entry of R, we check what the value of Q is at that point. We make one query to R, there's P, at the same point, and we output that, and everything looks consistent. Yeah? Okay. So this is a way of simulating this, right? So this is kind of why this random masking works. Okay. But unfortunately, this isn't sound, right? The reason this isn't sound is because what if the prover just like we've never checked that R sums to 0, right? The prover could just send us like any polynomial it wants to kind of massage the sum of P plus R to be the right thing, right? We never actually checked. Okay. So the most natural like interjection at this point is to say, but Jack, we have some check, right? We can just prove that the sum of R is 0, and then we're good, right? So, you know, our attempt at fixing this is like we have P, the input, we write down a random polynomial that's supposed to sum to 0. We write down a proof that the random polynomial does in fact sum to 0. And then we also write down the sum of P plus R, or the proof that P plus R sums to n. Okay, so this is complete and it is sound, but it's not zero knowledge anymore. Yeah, we're just getting screwed one way or the other, I know. Yeah. So the reason that this is not zero knowledge is because everything is kind of linear. So what I'll kind of say a bit more, but like what I mean is like say like you know you query the top row or the top entry of P plus R, sum of P plus R. that tells you like, actually I'll do bottom so I can reach. So the bottom, you query the bottom entry of this guy, that tells you like this sum plus this sum, right? If you query this one, it tells you this sum. Subtract the two, and you recover this, right? And now you need m queries to get this. So you've made 2 queries here to get something that requires m queries to the proof. So we're back in the same boat as before. Okay, so this doesn't work. Okay, so this is where the kind of new idea comes in to try and fix this. Okay, so people might be upset that I've been using rows so far. So if anyone prefers columns, we're going to talk about columns now. So this should hopefully be clear to everybody. It's equivalent to just think about column sums instead, right? So, write down all the column sums, do all the same stuff as before, right? This is like, hopefully very clear. You can just do column sums instead, right? But the interesting thing is, when you do column sums, well, what I'll say is, our kind of idea is to do the other proof using column sums. Okay, so you do the first proof using all the row sums. So the sum of p plus r is like, going to be row sums of p and r, and the proof that r sums to 0 is going to be over columns. Okay, and now there's no clear way to just like subtract off the 2 rows. Like you've kind of broken this linear homomorphism between these 2 proofs. Okay, so this is kind of one of the main like ideas of how to go about doing this. Okay, so we have row sums and column sums. These 2 things, like, kind of, you can think about, even if you have these column sums of r, in a sense, you need to have like m of them to kind of subtract off, right? It doesn't really help. They're just because they're orthogonal. Okay, so we're going to show more formally like why this actually works now. Okay, what this idea works. Are there any questions on what I've talked about so far? Please feel free to stop. So I'm going to slightly change our viewpoints on this column sum thing, just for the purposes of like, what we're going to do is not going to be heavy, but just for the purposes of explaining it on the diagram. So, sums over columns of R are equivalent to sums over rows of R transpose, right? You could consider taking the sums in another direction, or you can consider transposing R. Okay, so you can think about having these 2 sets of sums, which are both row sums now, again, okay? And actually, if you kind of squint, it's like, do we even need 2 proofs here now? So what we could do instead is we could give a proof of the sum, well, I'll just write it, of like P plus R minus R transpose, right? So this kind of consists of the same thing, but we're bundling everything into one proof. And the point is that like R minus R transpose, the sum of this thing over the hypercube, or over the square, sorry, the m by m square, is like structurally 0. It has to be 0, right? So what the proof is going to consist, I'll give you R, which gives you the ability to kind of query R transpose whenever you want to, obviously. And now, like, R is just a uniformly random low degree polynomial. And I give you a proof for P plus R minus R transpose. And the point is now the thing I've added on has to be 0 on the square. Like there's no longer like any need to check it. Structurally, it's 0. Okay. But we're going to hope that like somehow, and we'll hopefully show this, that like, adding R minus R transpose still hides all of these row sums of P, which is what we wanted to do. Okay.
So now R, does R have to sum to 0 now?
No, exactly. That's the point, right? So because R now is just a uniformly random polynomial, and then like when we take these sums, like R minus R transpose sums to 0, right? Whenever you take a sum, so like I guess whenever you take a row, it doesn't sum to 0. That's kind of the point. So like what the proof is going to look like, it's going to be a bunch of row sums of this thing, which will be like, for any entry, let's say the bottom entry, I peeked in the top first. So say we want this entry here. What's that going to be? It's going to be like this plus this minus like this. So that we wouldn't expect this to equal this, because we wouldn't expect the rows and columns to be equal, right? Yeah. So you don't have these cancelling away. But when we sum all of this up over the m by m square and we do our first check, we're going to get like, the m by m square minus the m by m square. It's going to cancel away. Yeah.
How do you make sure this like there exists a R such that it's plus R minus R transpose instead of like just a random different like matrix and which it so that you don't know if like the sum of P is
so like how do I know like that there's kind of like, do you mean like consistency between these 2 things, or what do you mean?
like, so maybe a adversarial can just instead of plus R minus R transpose, it just give you something else.
Yeah, at the end. Oh yeah, good. Okay, so I guess like kind of the soundness comes from like the same argument as before with like with the when we did this the bivariate sum check like the first time, like when I first introduced it when I just had P and I kind of argued like that, you know, remember you kind of did the green check. Like actually just go back. Just go back very quickly because we have time. Going up. So like this slide. So like now what the prover is giving you, right, is so they're giving you like a proof that looks like this, but instead of being just for P, it's for P plus R minus R transpose. Okay. And they also give you R.
Oh, they give you R.
Yeah. So they're writing R down. That's part of the PCP. Yeah. Sorry, I should have made that clear. Yeah. They like, yeah. So the proof doesn't just consist of this anymore. The proof consists of like this and R.
Okay.
So you're able to query R. And like when you're doing your verification, you will do all the same stuff we did here, except whenever you want to query P in this example, you query P plus R minus R transpose. So you like, you know, when you do this like row check, like when you want to check a random row, let me go back to the picture. So kind of like this, right? Like if you wanted to check a row of this thing, and here I haven't added in the R transpose yet, but like if I want to do a random check on this, I like, you know, I pick a location here, I check what it is, I query R on that row, I query P on that row, and I make sure everything agrees.
Sure.
But now you will do like, you know, pick a random location here, I'll query R on that row, I'll query R on that column, or R transpose on that row, whatever you want to think about it, and P on that row. I'll make sure it agrees. Yeah. Does that make sense?
Yes.
Yeah, good. Okay. Any more questions while I get back to?
What's the generalization to n variance?
Yeah, I'm going to talk a little bit about it when we get to the, because there's actually like one more step we have to do to make this work as well.
Sure.
No, but like
Yeah.
you basically like you can like think about if you had a cube, so like that would be like three variables.
Yeah.
Then you know instead of writing that, like you kind of write down like the row sums, like pick a direction in the cube, and like write down like all the row sums for every row in the cube. This will look like a square, right? It'll be like a table.
Yeah.
Right, so that's kind of like, that's the next step up of what we just did. We wrote down all the row sums of the table. So you just keep going, like you go in the opposite direction. Like from the three-dimensional object, you write down all the row sums of the four-dimensional object, and you just do this in every step.
Okay.
Yeah, but I'll talk a little bit more about it at the end. Yeah. Okay. So, yes, this is like kind of the main kind of trick we have to make everything work. There is like one more trick we're gonna have to do in a second, but I'm gonna explain kind of why this works a little bit more, like why we can simulate. We still have like what 20 minutes, do we? Yeah, cool. Okay, I shouldn't take too long, I think, to get through it, but I obviously want to make sure you understand. So I'm going to replace like R minus R transpose. So this is just R minus R transpose, but now I'm using like Y and X, and that's what this A thing is. So right, the prover is going to write down R for us, and then they're going to write down the sum of P plus R plus A, where A is like just this kind of R minus its transpose. So it's like a random kind of, we're going to call it like anti-symmetric. That's what we're going to call it. And this is complete and sound for like, kind of just for my answer to that last question, right? You can just do all the same checks as before and it all works. So now the question is to prove it's CK, right? So we're going to zoom in and we're going to look at the n by m square. So we're going to forget about the f by f square for a second. So the important thing here is now there's no low degree structure anymore. So this is just like a random, or okay, P isn't, but these are just like, you know, when we pick R on the n by m square, it's just a random matrix, right? Like if we go back, you know, R has to be like a low degree function, but when you only look at the n by m square, there's no structure there because it doesn't interpolate anything. So it's just a random matrix. Okay. Okay. So we're going to look at the n by m square. Okay. So we have P, our input. We have A, which is like R minus R transpose for some random matrix R. Okay. What does that thing look like? Well, you know, on the diagonal, R minus R transpose will cancel away. We'll have like uniformly random and independent entries in the lower half, which will like flip up to the upper half, or the upper triangle will be like the same with like a minus sign. Okay, this is like what this thing's going to look like, just by the fact that it's a random matrix and taking away its transpose. Okay. Okay, so say you make a query. Let's show this what applies to the right row sum. Say you make a query to like this row, okay, and the answer is gamma. Okay, what does that tell you? That tells you that you know this row plus this row is equal to gamma, right? This is kind of the same thing I was saying earlier on, but like I'm going to do it slightly more formal. So in maths, you know, you have like the row sum of P, that's all I'm saying here, plus the row sum of A is equal to gamma. You've got, and like the you know, when the simulator is going to simulate this, it's kind of going to just make up an answer for gamma because this is kind of look random, right? And the reason it's going to look random is because these A's are all random, right? So we've kind of added this randomness on. Okay. Now, let's say then the verifier wants to try and get rid of this randomness, right? What can it do? Well, it needs to like start figuring out these values of A, right? Because they're all like independent random bits. So it just needs to keep querying them, okay? So all that it can do is like, you know, query along the row n-1 times, right? Because until it's queried the last one, it still hasn't stripped away the randomness. And this whole thing still looks random, okay? Or query along the column because it's equivalent, okay? So the idea is basically that when you're the simulator, right, you make up gamma, and then the verifier starts, like, just say you're dealing with a situation where the verifier queries this and it works its way across. You make up gamma, just say a uniformly random answer. And then for all of the, say it's querying the column, for every entry in the column or the row, you just make up a uniformly random answer the whole way. And then when the verifier gets to the last one that's going to remove the mask, you need to get that one right? Because that one needs to agree with the actual sum now. They're going to have taken away the sum, right? Like afterwards, like if you answer it, right? It's just, you know, if you answer it and make something up, they can then go and like query the input and check if you're right? So they can check your work at that point. So you need to like make sure you get it right. So when they're about to query when they query the last one, you go and query the full row, right? But this is fine because they've made m queries now over here, and you're going to make m queries here to figure out the sum. So you're good. Okay. So in a sense, what we're saying is that like, you know, anything the verifier can figure out with m queries to the proof, they could have figured out with m queries to the input. Okay. This is essentially why this is zero knowledge. So you kind of only have to like, you only respond when everything, you get rid of the mask. I was just saying. Now, we didn't deal with the rest of the square though, right? We were giving the verifier this like low degree extension like thing, but we were only after kind of arguing zero knowledge on the small square. So we have like no reason to believe that this construction as it looks isn't ZK, but we couldn't show a simulator for it. We weren't able to. We can't find an attack. So what we did instead was we added in some extra stuff to deal with this. So what's the problem? The kind of problem is that like that argument we just made works because everything's very combinatorial. You just kind of have this like, you know, n by m square, everything's uniformly random. There's no low degree structure, right? But when you zoom out, all of a sudden the verifier has the ability to start like interpolating curves and stuff, right? Like right, you've got some randomness, you have quite a bit of randomness, but the verifier like, you know, can like pick a bunch of points and like pass a curve through something. And if you don't know about that, you're screwed, right? You need to make sure you're consistent with all this stuff. And now on top of that, this thing is like R minus R transpose. So this whole thing on the whole big square looks like this. And we weren't able to handle the two structures together. The observation we make is that you actually don't need this structure everywhere. So all that you want is like invariance of the sum on the n by m square. And this structure is giving you invariance of the sum everywhere. You only need it on the n by m square, right? So what we do is we want to try and scramble. Right, yeah, this is very, very artsy, I know. So we want to try and like scramble this structure everywhere apart from on the square. Okay, so how might you do that? Well, if you take a random polynomial, which is zero everywhere on the square, right? Now the whole thing, when you look at it, looks like a random polynomial that has this structure, but now like there isn't this low degree or this anti-symmetric kind of thing going on everywhere. Okay, so kind of one thing we have to do is figure out a way to actually like achieve this. Like, how do you send this part of the proof? Because now you're back in the same situation where you need to prove the thing the prover is sending to you actually is zero everywhere in there, right? Which is again, you have all the same problems we talked about before. So how do you do this? So basically what we use is the combinatorial nil stats from Novelon in the 90s. So basically what that gives you, I mean, you don't need to read all this, but what it gives you is like a way so the original result gives you a way to write polynomials. Like if you want to write a polynomial, which is like a low degree extension of zero, it gives you like a succinct way to write it in terms of some other polynomials. So these V's are kind of like, are just like kind of roots where you want them. So like you're putting roots in on the n by m square, and then you kind of have these polynomials of the kind of appropriate degree. What we show is that if you just pick random tx's and ty's, so just pick uniformly random polynomials of the right degree and slot them into this thing, it gives you a uniformly random low degree extension of the zero function. Okay. So what's the prover going to do? They're also going to send you tx and ty. And this is not going to affect the sum, right? And you're going to do the sum for this whole new thing, right? So your kind of final mask is like a random polynomial minus its transpose plus like a random low degree extension of 0. Okay. So this is like this is the full like construction of the bivariate case. So you basically give, as I said, random polynomial, random polynomial, random polynomial. And these ones are just to allow you to construct a low degree extension of 0. And again, you don't need to check that it's a low degree extension of 0. You know structurally that it is one, right, by this theorem. So yeah, this is the full construction. I'm not going to talk about how to like actually simulate the low degree structure because that's quite involved. And what I will quickly say to get at Klein's question from earlier is like what happens in the full multivariate case, right? So now P is like some like m-variate polynomial, right? And you need to like kind of try and do all the same stuff as before. So you're still going to write down like a random polynomial R, which is like m-variate, and now you're going to have like kind of one of these polynomials for each degree that's going to have the null-stats goes. And the way you generalize this notion of like columns versus rows is you reverse the order of summation, which is equivalent to just flipping the order of like the entries. So it's kind of right in this one you're kind of summing like kind of like row by row by row by row, and this one you're kind of going column, like you're kind of going backwards in a sense. So this is like a transposition kind of on steroids or something, which is kind of flipping, right? There probably are like this is not special. I think there are other ones, other permutations that will work, but it's quite simple. Yeah, that's the full thing. And then there's also more complication, unfortunately. So you also need to handle the fact that now, kind of as I mentioned earlier, when I talked about what sum check looks like when you go up in dimensions, you have like kind of for each dimension, you have a proof in a sense. So you kind of say like, you write down at the top, you write down all the sums where you kind of fix the first variable for every fixing of the first variable. Then you write down all the sums for where you fixed like the second two variables for every fixing of the second two variables, and so on. You write all these things down. So now when you want to simulate, you have to like, it's not just enough to kind of say, oh, like the row sums agree with the input. You have to make sure that like different levels of this stack agree with one another and like all these kinds of things. Okay. And like the completeness and soundness still works, but like showing you can simulate this is complicated. And I think the final thing I'll say before I put my final slide is like that also when you're dealing with the next, so like this, I've kind of been thinking with NP in our heads here. When you're thinking about next, you need to do all this stuff computationally efficiently. This kind of gets at your kind of point from earlier. So like not only like kind of what I said earlier about like I talked about like writing down all of Q. Like you just kind of write down a polynomial Q that sums to the right thing, and then you kind of do a bunch of stuff. That's not possible anymore when you're in the next case. And like there are algorithms that let you kind of make up a polynomial as you go. Yeah, I'll finish there. So as summary, like this is what we get, as I talked about before. So we get like perfect zero knowledge PCPs for NP with poly proof length and constant query complexity. There are the two papers if you're interested. I only got to talk about the first one today. Yeah, there's a couple of future sessions, but I think I spoke about them earlier. So yeah, thank you very much for coming and your time. And yeah, cool. Any questions?
Aren't there more